Welcome back. We are going to do an exercise in this segment, so let me go ahead and just set that up for us. So here's the exercise. So remember last time, so we started with y equals mx plus b, and in our first least squares estimate, I threw away the intercept and I said, okay, let's just go ahead and assume the intercept is 0, and let's just fit y equals m. In this one, we're going to throw away the slope and just do the intercept. So the exercise is to derive the least squares estimate for fitting the following equation of a line, y is equal to b. So just a horizontal line. The slope is determined for you. It's horizontal. And you have to figure out what is the intercept, this value. One unknown here. So if you want the challenge, go ahead and pause the video now and try to solve this. I will say it's going to follow the same form. Figure out what the vertical distance is. You should be able to write out what delta is for every point for this model. And then write the quadratic error function e of b now should be the sum of all those deltas squared. Differentiate it, set equal to 0, solve, and then tell me what the value of b is as a function of the x's and the y's in the data that you are provided. Okay, so if you want the challenge, go ahead and do that. If you want a little bit of a hint, hang out for a few minutes, and I'm going to help you derive the deltas in the error function, and then I'm going to ask you to go ahead and solve by setting up the differential equation and solving. Okay, so let's go ahead and figure out what the vertical distance is. All right, so again, vertical distance, same as before, right? I'm still the vertical distance for each point delta sub I. So what is that? Well, let's see. So first of all, what is the vertical distance of that point? Well, that hasn't changed. It's still yi. Nothing changes. The point is the point. And now the question is, well, what's the vertical distance of that line right there? Well, the equation of the line is what? Y is equal to b. So that value must be, well, b. So that delta must be just b minus y. Okay, so think about it this way. My line is y equals b. How far am I from the line? Well, I'm b units away. So if y sub I is b, well, the error is 0 because I'm on the line, like this guy right here. And if it's not, it's just the distance. Okay, so that's the delta, just the vertical distance from the line. All right, that's easy. And so what do I want to do now? I want to minimize the square of all of those vertical distances for every point xi, yi. Now notice xi doesn't show up here. Why? Well, because that vertical distance doesn't depend on x. Right? Why? Well, because the line doesn't depend on x. The line is completely determined by the vertical distance, and so every vertical distance is just b minus y, b minus y, b minus y, b minus y, etc., etc. Okay, it's no problem. We don't care. We don't care what's in here as long as it's something we know, and it just happens to be the y's. So your job now is to minimize this for b. Okay. All right. So pause the video now and go back. If you don't know how to proceed, go back and re-watch the previous segment on how we did this for the slope, and try to do the same type of thing. All right. So let's see now. So I hope you got that. So there's my error function. So what do I want to do? Well, I want to unpack this, right? I want to unpack it to get that b out of there. Well, we know how to unpack it. There's a polynomial right there. Let's go ahead and unpack it. So what do I have here? Well, it's b minus yi times b minus yi. So that's b squared here plus yi squared there. It's positive because that's a negative sign. And then minus twice the product of the two. Okay, so if you don't see that, just write b minus yi times b minus yi and do the polynomial expansion. Okay, so this is starting to look good already, by the way, because I've got a b squared term, and I've got a b term, and I've got a constant term. That's already starting to look like a parabola, so I'm already feeling pretty good about this. Now I got to get them out of the for loop, outside of that summation. So the good news is that's not indexed on I. Of course not. There's only one b. That's not indexed on I. There's only one b. And so let's unpack this summation. All right, so I've got a b squared times what? So it's well, there's nothing there. Well, there is something there. There's just a 1. So what am I going to do? Let's ignore these two terms over here. I'm going to compute for I equals 1 to n, the sum of b squared, b squared, b squared. So that's b squared plus b squared plus b squared n times. Well, that's just b squared times 1 plus 1 plus 1, or b squared times n. So there's the first term. Now here I've got a minus 2b that is not indexed on the increment I. So that's going to come out, and I'm going to have the sum from I equals 1 to n of y1 to yn. So there's my linear term. That's my quadratic term. And then my constant term is over here, y1 squared up to yn squared. It's just that thing. There's no b there. There's nothing to factor out. Again, this is starting to look pretty good. I've got a quadratic term here, b squared, something that I know, n. I've got a linear term here, constant, something I know, and I have a constant term. So the error that I now want to minimize in b, that's my model parameters, is equal to n times b squared, n is just the sum of all those ones, of course, plus some constant, I'll call it alpha this time, instead of using a and b because it'll confuse me with that b. Alpha times that term right there, the sum of all the y's, plus some constant beta, which is the sum of the squares. All right, this is starting to look really good. I seem to just have a parabola again. I've got a constant times b squared plus a constant times b plus a constant. All right, let's go back and just ask ourselves the question, is it this or is it this? Well, this is when the term on the squared term is positive, and that's when it's negative. So what is n? Well, it's just the number of data points. Can that be negative? Of course not. So we're guaranteed that that's what we have. Good, because I don't know what to do with that thing over there. Since we have a negative, well, now I can simply differentiate this, figure out where the derivative is 0, the tangent is 0, and that's going to be my b that minimizes that quadratic error function. All right, let's compute a derivative. We know how to do this because we've already done it. It's just a different term here. So the derivative of this with respect to b is going to be what? It's going to be 2n times b to the power 1, b. This is going to be alpha times b to the power 0, alpha. And of course, the derivative constant with respect to anything is equal to 0, so that just goes away. So now I've got a very simple expression, 2n, n is the number of data points, alpha is the sum of the squares of all the y's. And what do I want? I want to know, where is that equal to 0? What am I asking? Where is the derivative equal to 0? That tells me where it's at a minimum because I have a parabola that looks like this. All right, well, that's pretty easy to do. Set 2n b plus alpha equal to 0. So I'm going to just expand it out here so you can see it. I got 2nb plus minus 2 times the sum of all the y's is equal to 0. So what do I have here? Well, this is known. I got two values of 2 here. Those are probably going to cancel themselves out. I've got an n over here that I know. That's just the number of data points, and I have a b. Well, let's just go ahead and solve that simple equation for b. So b is equal to what? Well, I'm going to take this term and bring it over to the right-hand side. I've got a 2 on the left, 2 on the right. Those cancel out. I divide both sides by n. I've got 1 over n times the sum of all the y's. Okay? There it is. There's my least squares estimate for fitting a zero slope line to a line with an arbitrary intercept, a horizontal line. Okay? Does it make sense? What's the intuition here? Well, let's see. So what is this, first of all? It's 1 over n, there's n data points, times the sum of all the y values. It's just the average. I'm just computing the average of all the y's. So now let's go back to our intuition. I tell you I got a bunch of points, and I want to draw a y to it that minimizes the average distance to each point. Yeah, sure, taking the average value of all these y's makes perfect sense. It's going to sort of go through these things. Some of them will be a little big, some will be a little bit small, and I'm going to simply compute the average. So the least squares estimate actually seems to make sense here. We have good intuition as to why we're doing this. Okay? So that's nice. It's always nice when you get these sort of answers and you can look at them and say, yeah, that sort of makes sense. Or maybe I can't make sense of it in the complex, but in the degenerate case where you have only a couple of data points, it makes more sense. Okay? All right, so now we've seen two things. In both cases, in one case we fit the equation of the line y equals mx. In the other one, we fit the equation of the line y equals b. In both cases, we did exactly the same thing. We computed the vertical distance between the data point and the line. We took the square of all those and summed them up and packed that into a quadratic error function. Quadratic because of the square. Yeah. We notice that that's a parabola. So we differentiate that quadratic error function with respect to the unknown, either the slope or the intercept. We set equal to 0, and we solve for the unknown, either the slope m or the intercept b, and that gave us our parameter that minimized the error function. And again, remember that the reason we're doing this instead of doing some brute force search over all the spaces, it's super clean. The error function's a parabola. There's no reason to evaluate any points other than where the derivative is 0, because that's where I know the answer is. So that's called a closed form or analytic solution. Very clean, very nice, and very easy to solve. Now, what we want to do now is start thinking about, what if I have more than one parameter? Because right up until now, everything's been relatively straightforward. I just do a little bit of algebra, I compute a first derivative, and then I solve a simple linear equation. Should be pretty easy. So what happens now when I have two parameters? How am I going to do that? Well, that's what's going to come next. All right, so we'll pick it up in a few minutes. See you soon.